In machine learning applications, we rarely can predict outcomes perfectly. For example, spam detectors often miss emails that are clearly spam. Siri often misunderstands the word we're saying, and your bank at times thinks your card was stolen when it was not. The most common reason for not being able to build perfect algorithms is that it is impossible to do so. To see this, note that most datasets will include groups of observations with the same exact observed values for all predictors, but with different outcomes. Because our prediction rules are functions, equal inputs implies equal outputs. Therefore, for a challenge in which the same predictors are associated with different outcomes across different individual observations, it is impossible to predict correctly for all these cases. We saw a simple example of this in a previous video, in which for any given x, you will have both males and females that are x inches tall. However, none of this means that we can't build useful algorithms that are much better than guessing, and in some cases, better than expert opinions. To achieve this in an optimal way, we make use of probabilistic representations of the problem based on the ideas presented in our regression course. We share a link to this course in our course notes. Observations with the same observed value for the predictions may not all be the same, but we can assume that they all have the same probability for each class. We will write this idea out mathematically for the case of categorical data. We use a notation capital X equals little x 1 through p to represent the fact that we observe values little x1 through little xp for features capital X1 to capital XP. The probabilistic approach assumes all the observations with these features have the same probability distribution, as opposed to outcome y always taking the same specific value. In particular, we denote the conditional probabilities for each class K like this. To avoid writing out all the predictors, we will use the bold letters like this. We will also use the following notation for the conditional probability being in class K. Now, going forward, we'll use the small p notation to represent conditional probabilities as function of the class. Don't confuse this p with the p representing the number of features. These probabilities guide the construction of an algorithm that makes the best possible prediction. For any given x, we will predict the class K with the largest probability among the p1 through pk of x. In mathematical notation, we can write it like this. In machine learning, we refer to this as Bayes' rule. But keep in mind that this is a theoretical rule, since in practice we don't know these probabilities. In fact, estimating these conditional probabilities can be thought of as the main challenge of machine learning. The better estimate of these probabilities, the better our predictor. So, our predictions depend on two things. How close are the maximum probabilities to 1 or 0, perfect certainty, and 2, how close our estimates are to the actual probabilities. We can't do anything about the first restrictions, as it is determined by the nature of the problem, so our energy goes into finding ways to best estimate the conditional probabilities. This first restriction does imply that we have limits as to how well even the best possible algorithm can perform. You should get used to the idea that while in some challenges we will be able to achieve almost perfect accuracy, like with the digit readers, in others our success is restricted by the randomness of the process. With movie recommendations, we will see this. Before we continue, it is important to remember that defining our predictions by maximizing the probability is not always optimal in practice and depends on the context. As discussed previously, sensitivity and specificity may differ in importance. But even in these cases, having a good estimate of the conditional probabilities for each class will suffice for us to build the optimal prediction models, since we can control the balance between specificity and sensitivity however we wish. For instance, we can simply change the cutoffs used to predict one outcome or the other. In the plane example, we may ground the plane anytime the probability of malfunction is higher than 1 in a million, as opposed to the default 1/2, used when error types are equally undesired. For binary data, you can think of the conditional probability as the proportion of ones in the stratum of the population when we observe little x. Many of the algorithms we will learn can be applied to both categorical and continuous data due to the connection between conditional probabilities and conditional expectations. Because the expectation is the average of values y1 through yn in the population, in the case in which the y's are 0 or 1, the expectation is equivalent to the probability of randomly picking a 1, since the average is simply the proportion of ones. As a result, we often only use the expectation to denote both the conditional probability and the conditional expectation. Just like with categorical outcomes, in most applications, the same observed predictors do not guarantee the same continuous outcome. Instead, we assume that the outcomes follow the same conditional distribution. We will now explain why we use the conditional expectation to define our predictors. Why do we care about the conditional expectation in machine learning? This is because the expected value has an attractive mathematical property. It minimizes the MSE. Specifically, for all possible predictions y hat, the conditional expectation minimizes the expected squared loss. Due to this property, a succinct description of the main task of machine learning is that we use data to estimate this conditional expectation for any set of features. Of course, this is easier said than done, since the function can take any shape and p can be very large. To see this, consider a case in which we only have one predictor, so it's simpler. The expectation e of y given x can be any function of x, a line, a parabola, a sine wave, a step function, anything. It gets even more complicated when we consider instances with large number of features, in which case f of x is a function of a multidimensional vector. For example, in our digit reader example, there's 784 features. The main way in which competing machine learning algorithms differ is in their approach to estimating this expectation.